Hello, welcome everyone. Thanks for joining us. This is our PowerWeb Lunch Lecture series, which goes on every month or every couple of months, depending on the calendar. I am Francesco Lombardi. I'm assistant professor here at Delft in the Faculty of Technology, Policy and Management, but I also collaborate in this cross-faculty institute where we try to tackle challenges that require cross-disciplinary collaboration. We aim to support in this institute the energy systems of the future, intelligent, inclusive, and integrated. There's a broad range of people who contribute to the institute, but really most of the activities run through Lily Lee, our managing director, Alex Niago, who's here, our program manager, and Peter Palensky, the scientific director. And I'm the coordinator of the lunch lecture series. Yeah, we do all sorts of things, but as I said, we try to deliver energy systems that can be intelligent, integrated, and inclusive. And today's lecture focuses a bit on this third pillar, the integration aspect, because we're going to talk about hydrogen, and specifically what happened with hydrogen. There was a huge hype a couple of years ago. Now, not so much anymore. Why is that? And what is the current outlook for hydrogen? And we're going to hear all about it from Marjolijn Goorden from Eneco, who's the hydrogen expert at Eneco. So no one can tell us better than her everything about this fascinating topic. So without further ado, I'm going to give the floor to Marjolijn, but please follow us. You can find us on LinkedIn and other social media. So if you want to stay tuned about future seminars and other opportunities, do follow us. So Marjolijn, please educate us and entertain us with your lecture, and thank you for joining us again.
I think I'm on, yeah. Hi, everyone. It's fun to be here. I also studied here. Well, not specifically here. I did mechanical engineering, so I was at the neighbor building. Graduated, I think, 7 years ago. But good times. So nice to be back. And today, I'm going to hopefully discuss with you as well electrolysis in the Netherlands. So it's about the local use and production of green hydrogen, what to do with it. So I don't know if you're all hydrogen fans or if you're deeply in the topic or maybe just read something about it. You might have read in the past 5 years, a lot of projects were pronounced. Tens of megawatts, hundreds of megawatts, even gigawatts in the Netherlands. And you might have noticed that actually almost none of these projects are actually built. Part of them are paused or even pulled the plug. So what happened here? I myself, I work at Eneco within strategies, hydrogen strategies. We also pronounced big projects. Eneco Electrolyzer on the Maasvlakte, 100 megawatts, then 200 megawatts, maybe even 800 megawatts. And where are we now? What I want to do with you is first completely zoom out. So how did this all started? The whole hydrogen transition, actually, the whole hydrogen economy was being announced. Do we actually need it? What sectors need green hydrogen? What are the end products that these sectors provide? So it's good to have these insights because if you use green hydrogen, there comes a whole value chain afterwards, and then you have your end product. So how do we get there? Is it really necessary to use green hydrogen? Are there better alternatives? Energy is in the commercial sector. That means we need to make money. And that means if there's a cheaper alternative that fits the requirements, that's the one we're going to pick. And if that's not green hydrogen, then it's not happening. So, nice image. What we see here is an overview of the current use of fossil fuels in the Netherlands. Let's see if my pointer works here. Oh. I think I accidentally switched off the screen. One slide back, yeah. This works, yeah. So fossil fuels in the Netherlands, we currently use, here I can also use, I'll use it here. It's a bit difficult, let's do it, I'll do it with my hands. We have 3, natural gas, of course, crude oil and coal. coal is currently almost only being used for production of steel. So most coal power plants are shut down after 2030. All of them has to be shut down in the Netherlands. So coal, a bit for direct heat and power, mainly for steel. Natural gas, of course, directly used for heat in industries, houses, and directly used for power in natural gas power plants. And then we have crude oil. By far the biggest part of our crude oil goes to refineries and is split within these products. So we see big one, gasoline, kerosene, diesel, marine fuel oil, and two of them, naphtha and aromatics. This is important. I'm gonna get back on this later in the presentation. Naphtha and aromatics are used as feedstock for the chemical industry. The Netherlands has quite a big chemical industry. So it means the aromatics and naphtha is not being used for final energy, but feedstock, so an actual product. And then over here, actually, you see this entire chemical industry in the Netherlands. And you might have noticed that I split this chemical industry two parts: base chemicals, the easy chemicals like the C4, C5, C6 configuration molecules, and the specialty chemicals. And these specialty chemicals are used for, well, here you see an overview of examples of products that we make with these chemicals. So everything that happens here is molecules. Now, on my next slide, this could be a system fully independent of fossil fuels. It only consists of renewables. And let's go one slide back. The right side of this system is approximately the same. So we have our same chemical industry. We can still make aviation fuel, eSAF, you see here. We can still make marine fuel, methanol, shipping fuel. We can still make heat and power from methane, hydrogen, power, of course, directly from wind and solar. So with only wind and solar, we can make both heat and power. Through electrolysis, carbon capture, gasification of biomass, we can make more molecules, use that for complex fuels, so shipping fuel, aviation fuel, these things. And we can also use that for feedstock for the chemical industry, make both the base chemicals and from the base chemicals, the specialty chemicals. Now, so that's hopeful. So technology is there. We can actually do this. But why is it not being done then? That is because maybe you might have heard hydrogen can be made cheaper in, for instance, Australia, Morocco, Canada, Oman. Actually, every place in the world that has a lot of space and a lot of sun is a good place to make hydrogen. But then you have to transport it here. Hydrogen is not very suited for transport by ship. It's very expensive. You have a lot of leakage. You have to compress it, which makes it energy intensive. So not very well suited for shipping. What is, however, well suited for shipping are these intermediate products. Methanol, we ship methanol around the world. We've been doing it for decades. Pretty easy to ship. Same goes for ammonia. Methane, LNG, we now ship that. These base chemicals are being shipped all around the world for years. So where I'm going to is if it's cheaper to import these intermediate products by ship, and energy and also the chemical sector are commercial sectors, then why buy the locally produced molecules? And that is a bit what's happening at this moment. And then you could argue, but then use hydrogen in the form of hydrogen. So if hydrogen is very expensive to ship, then if you need hydrogen in its pure form, it's better to produce it locally because it's more expensive to ship it. What sectors actually need pure hydrogen in the form of hydrogen? That's almost none. We see entirely above in the right corner, hydrogenation. That's the use of pure hydrogen added to products. It's being used in the food sector in the Netherlands to make mayonnaise and butter. It's being used mostly to make oily substances thicker. We should use it a little for eSAF. So eSAF, would consist in a process of 97% methanol, 3% pure hydrogen. That's only 3%. And then, of course, the oil refineries, they use hydrogen for desulfurization. But if you don't have fossil fuels in your system, you can close down all your oil refineries. So that's also not a sector that would need it in this end game system. Now I want to dive in deeper on these prices. So yes, we need hydrogen. So specifically for the chemical sector, they don't have any alternative because they need molecules. So they need hydrogen, carbon, either from electrolysis or biomass, but they need molecules. Long flights aviation, so intercontinental flights, seems like it's quite tough to electrify that. Maybe you've already found a solution, but I'm not aware of it yet. So not the short flights, but the long flights. Looks like ESAF is the best suited solution for this. Therefore, you need hydrogen molecules. Ammonia, of course, that's also a molecule. We need it for fertilizers. You make it from nitrogen, from air, and hydrogen. So yes, we need hydrogen in a couple of sectors. Where does it come from? We could produce it, of course, in the Netherlands on land, all these projects that were being announced. We could produce it offshore. We had Demo 1 and Demo 2 in the Netherlands announced a couple of years ago. I've also worked on that. Could be done. We could import it. I already mentioned this. Maybe blue. So natural gas and carbon capture. Let's see what it does. So this is an outlook for the prices for green hydrogen equivalent, I call this, in 2030. And what we see to start with, offshore is not looking well. A big pro of offshore hydrogen production is that you need smaller electricity cables from your offshore wind to land, and these electricity cables are very, very expensive. However, what is even more expensive is to put your electrolyzer offshore on a platform, install it there, maintain it there, operate it there. These costs are even higher than the cost that you bear on the cable. So the total system becomes more expensive, a lot. We could do it on land. Current estimations now are 12 euros per kilogram production. And you see how it's built up here. Big part is power. So we didn't know this 5 years ago. Actually, we couldn't know this 5 years ago because 5 years ago, Eneco developed Hollandse Kust Noord, which is an offshore wind farm, for 43 euros per megawatt hour levelized cost of electricity. Currently, we're at 90. So prices for offshore wind went through the roof. Electricity is a big part of your electricity costs, or a big part of your hydrogen cost. That means hydrogen becomes super expensive in a country where power is super expensive. Big part is capex, and with capex I do not only mean just the machine itself, but also the whole plant around it, safety measures, parking spots, installation, commissioning, all these things. Big part of hydrogen production costs. We have grid costs, currently pretty expensive in the Netherlands. However, there are some policies in the making that should give a discount on flex assets. Hydrogen electrolyzers are seen as a flex asset, so this could go down, but yeah, it's not going to make a very big difference. However, it's something. Some other OPEX, hydrogen transport. And then let's look at import. So here, we can compete with import. We're approximately at the same price. When I made this slide, the cheapest way of importing seemed to be ammonia. So you produce hydrogen, for instance, in Oman, convert it into ammonia, ship it here, crack it back. That's this thingy. So in this 4.50 € is the production of ammonia in, for instance, Oman, and cracking it back to hydrogen in the port of Rotterdam. So that means you could make it for, let's say 7 euros subsidy free. So many of these Middle Eastern countries, Egypt, get a lot of subsidy, China as well, to get hydrogen going. But subsidy free would be around €7 if you would buy everything now and install it, and then in 2030 run it. So you might have read €3 per kilogram China. That's probably 5, 6, and then half of it's being subsidized by governments, which is a good thing, of course. Then we have blue here, a lot cheaper. However, I think these CCS costs, if I would make a new update, would be a lot higher than they are now. At these times, the Aramis pipeline from Shell and the, I don't know the name of the other pipeline, well, the two big carbon pipelines where you could inject your CO2 in, the first estimates of the injection cost were pretty, let's say, optimistic. So, well, let's say we would end up here a lot lower than green. However, this is not considered RFMBO compliant, so you cannot use it for your RED III European legislation. You cannot make ESAF of it, and well, you could, but you don't get the credits. And then we have gray, by far the cheapest form of hydrogen. So if you look at this picture, then why not make it here? Because it gives us energy independency. We can compete with import. We're approximately at the same price. That is because this is the competition with hydrogen derivatives. So as I just mentioned, very, very little end users need pure hydrogen. Most of them need methanol. That's almost the entire chemical sector. You make methanol and then your base chemicals, then specialty chemicals. Fertilizers need ammonia. ESAF, production process, 3% hydrogen, 97% methanol. Marine fuels also looks like that would be either ammonia or methanol. It's very, very tough to compete with hydrogen derivatives, local production versus import. And that's what you see on this slide. So on the most left, we have production of methanol here in the Netherlands. Import of methanol and gray methanol as a reference. Import is just, it's a big gap. And the same goes for ammonia. And that is why none of these projects, well, except for Holland Hydrogen 1 from Shell, is not built yet, because it's not that they don't want to or because they can't. It's because nobody wants to buy their hydrogen. Because these import projects or these import prices, they're actually already being sold to Dutch off-takers from Australia, from Canada. Maybe you know Power2X, company that wants to start an ESAF factory in the Maasvlakte. They're looking in import methanol from Canada, US, a lot of different places in the world where these projects can be made a lot cheaper than here. So we did the same thing. We went on the market with our hydrogen production plant or electrolyzer to many different off-takers, also the off-takers that were obliged in 2030, so aviation sector, marine sector. They said, yeah, we have cheaper alternatives. So either you go below this import price, or we're not going to buy from you. And if we go below the import price, we make losses because that's below our production price. This is actually something I've already told you in the first slides, but it's another overview of the typical sectors that are likely to use hydrogen as they greenify. So I mentioned chemical sector, ESAF, marine fuel, steel. Maybe some of you thought of steel. We have quite also a large steel sector, of course, in the Netherlands, Tata Steel. If you want to make green steel, you have to do direct reduction of iron. So iron ore, reduce it with something else, not coal, hydrogen in this case. And then you can, with electric arc furnaces, make steel of it. But how do we make steel now? So yeah, we make it here, but we import iron ore, we import coal, we do the reduction here, and then make steel of it. Our iron ore, a lot of it comes from Australia. Australia is a very, very, very suited country for cheap green hydrogen production. So what Australia hints on is do not buy the iron ore from us, buy reduced iron from us. So we mine the iron ore, We reduce it locally with cheaper green hydrogen. We ship reduced iron to Europe because you're good at steel making. And there you only need electricity for the whole steel making process. So then again, no need for local production of hydrogen, even for the steel sector, because our intermediate products, reduced iron, can be imported cheaper than that we can produce them here. And these processes, they do not exist yet. So it's not that we have a very deeply rooted DRI plant here with all the knowledge and all the skilled staff. We have to build it from scratch. The entire world has to. So then you build it in the region that is most suited for it. And by most suited, I mean lowest cost. Road transport, I mentioned. I think 95% of road transport should be electrified. It's for many, many vehicles the cheapest option. It's also good for flex. These are good flex assets, potentially. If you cannot electrify your road transport, methanol seems the most likely, even more than pure hydrogen. And then I mean like heavy trucks and these things. Could be that this is going to look differently and that pure hydrogen is the cheapest option. Then here there's a opportunity. So for a small amount of road transport, there is an opportunity for green hydrogen utilization in the form of green hydrogen, and therefore for local production of green hydrogen. Fertilizers I discussed, intermediate product is ammonia, cheaper to import. And then we have power balancing, dispatchable power, and others. So I mentioned food, not in steel making process, but in metal product making process, and glass and some high temperature heat. These are sectors that are most likely to have the cheapest way of making them sustainable through hydrogen. But this is a small amount. So this is not even 2 gigawatt of electrolysis. And the government announced we need 3 to 4 gigawatt in 2030, scale up to 8 in 35, and end somewhere in the 2030, 40 gigawatt of electrolysis end game. I think we're going to, if we can build 2 gigawatts, we did well. Personally, I don't think we need more. Dispatchable power, this is very, very difficult. If you do it with hydrogen, locally produced or imported, it's both super expensive. Biogas is a very nice alternative, but we have problems with availability. Then other institutes say, well, we currently have problems with availability, but we should import more biomass from other countries, make biogas here, or there's a whole charted biomass, there's much more available globally than we know now. Could be. I'm not sure about that. What we're currently seeing is that gas-fired power plants are being ramped up in government plants. So not physically, but in most plants, the focus is more on natural gas, which is a pity now. And of course, everybody's talking about it. Nobody's building it because it's not commercially available. The SMRs, the small modular reactors, could be nice. However, not on the market yet. Yeah, so here, this is one of my last slides. What do we do with hydrogen in the Netherlands? How much do we need? How much are we going to make ourselves? Let me start off with this. If we are going to make it in the Netherlands, this is highly, highly dependent on policies. Everything in the energy transition is, because as I mentioned, it's a commercial business, energy. Green is, at this moment, more expensive than gray. So let's say the low-hanging fruit in the energy transition is being picked. What we're left over with now is more expensive than our fossil alternative. That means a commercial sector is never going to move by itself. That's not how commercial sectors work. So you have to push them with policies. You have to do offtake obligations for green products or give subsidies to make these commercial industries move towards a more expensive alternative. So here we have energy policies on the horizontal vertical axis. So we could do this in Europe. We could say, okay, you have a green offtake agreement, you need green power or green molecules or green import, or your end product needs to be green. What is very likely to happen if we only do that is that a lot of big industries say, okay, then we'll leave Europe. That's fine. We'll just make our product somewhere else and import the product. Even if you do something like CBAM, so that you say if you import your product, it still has to be green according to European legislation. It's probably cheaper to make these green products in the countries I mentioned before. In the US, China, Australia, maybe Canada, Chile, the countries with a lot of solar power. These industries, if they have to switch from fossil to green, a lot of them have to make such big changes that they have to almost build up an entirely new plant. So why not build it up somewhere where the power is cheaper? So then if you do not want that to happen, you also need industry policies. You need some mechanism to keep your industries here. That's also going to play a big role in how much hydrogen we're going to make in Europe. Do we want industries to remain here, or are we okay with them leaving? And do we want to produce green, or are we okay with fossil? What's happening now is, well, let's not make this too much of a politics discussion, but in the previous coalitions in the Netherlands, the aim was let's go green and the market is going to solve this, but this world does not exist. As I mentioned, the market will solve it up to the point where they can make money out of it. Now we're behind that point, so that's where it stops. So if you want to go green, you have to force this with policy. This is very little policy. Let's leave it up to the market. And we don't mind industries leaving. These are their own choices. I think 0.8 gigawatt, 800 megawatts of electrolysis we're going to end up with in the Netherlands, endgame 2050. If, however, we're going to push for green policies, and we really want these industries to stay, so if we want to keep our chemical sector, and not only the specialty chemicals, but also production of base chemicals, even production of feedstock, so methanol, ammonia, these things. If we want to produce aviation fuel in the amount that we do now, we're a net exporter of aviation fuel. We make 3 times more aviation fuel than we use, the rest we export. If we want to keep that production capacity, also with marine fuel, fertilizers, all these things, and we're going to make this completely green, we need, indeed, this 40 gigawatt of electrolysis. I personally find it very unlikely that we're going to push to make everything, all molecules in the Netherlands when importing is cheaper. So if you do this, you either need a lot of subsidy, that's public money, or all your products will become a lot more expensive. That's also kind of public money. Then you just have to pay more for everything you buy. And the energy transition is already going to be pretty expensive. So let's say we want to keep industries here, but we're okay with importing intermediate products. Then we end up around somewhere here. This is where I personally think we're going to end up, somewhere in this area. Or we say, no, we're okay with some industries leaving. However, the industries that stay, we do want to make all the feedstock ourselves. Then you end up higher. Yeah, I don't think that's very likely. It's not with a global market that we have on all these molecules. It's very disruptive to do something like that. So this is my estimate of somewhere between 0.8 and 40 gigawatts we're going to end up. This slide, let's quickly go through it. How am I? 2 more minutes. Okay. So what I try to picture here is a possible system for 2050. Because sometimes you hear, yeah, we need offshore hydrogen production because we cannot land all the offshore wind. So then we need to pull cables through difficult ecosystems, but that is only if you go above 50 gigawatts of offshore wind. In this system, we end up with 40 gigawatts of offshore wind. One of the scenarios, I think it's from either CE Delft or TNO, is an estimation of 105 gigawatts of solar in 2050, around 10 gigawatts of wind on land. This is the landfall of offshore wind, where we can land the wind. TenneT has made a claim, I think, a couple of years ago. We think we can land 50 gigawatts, but after that it becomes very complicated. Here, the 2.1 gigawatts of electrolysis I mentioned before. So industries, actually the end of the value chain, that's what stays here, but the intermediate products are imported if that's cheaper. And then, well, here you see small balance. It's not very important. I also added some biomass to the system. There are batteries in this system, but it's not supply or demand. It's balancing, so you don't see it in here. I added some biomass for some extra balance baseload power, and a lot of import of ammonia and methanol. Yes. So we would need around 63 megatons per year of import of these intermediate products to keep all the production of end products that I mentioned before in the chemical industry here. As a reference point, we're currently importing 43 megatons of crude oil per year in the Netherlands. So we would have to ramp up our import terminal capacity by approximately 50%. That's quite something. Not sure if that will happen, but it's a scenario, and it's actually more to show that I don't think you need over 50 gigawatts of offshore wind. I think you could do it something like this, with more focus on import of molecules and focus on electrification on land. So that's a point I didn't make yet, but very important to tell you. Everything that can be electrified, it's 99.9% of the time the cheapest and best and most efficient option. So actually you only use molecules if you cannot electrify, or if you have a lot of trouble with balancing, you need power immediately or you need it for a long time. Yes, so this was it. I talked, I think, 30 minutes straight. Questions or notes, something you want to discuss? Oh, thank you.
Yes, thanks a lot for the super insightful presentation. I'm sure there are plenty of questions. I already see some. I will need to bring you the microphone because we are recording, and if you don't speak in the microphone, we don't hear anything. So let's go to the first question over there.
Thank you for the presentation. It was a couple of very good insights. I thank you for it. I had a couple of questions, specifically about the slide in which you proposed the alternatives for hydrogen, for green hydrogen, I think.
This one or the one at the beginning?
The previous one, yeah. One of the, yeah, exactly. So for both methanol and ammonia, I see that the biggest chunk of the price that you're saying is again the price of hydrogen.
Yes.
Since the previous slide, we already seen all the prices for green hydrogen. I assume these hydrogens are not green.
Yes, this is green hydrogen.
Okay, and
but
so
what you see here, I think this is what your question is about. These are the same, right? But this is hydrogen converted into ammonia, shipped here, cracked back to hydrogen. If you don't do all of that, then you're here. So let's say you can produce.
Still, it looks like half of the, so like 12 euros, it's like 6 euros before the
7, 6, yeah.
Yeah, but here, for example, for the ammonia, the whole thing is 2 euros.
Yes, in ammonia. So this is kilogram ammonia, and what we saw before is kilogram hydrogen. So ammonia has a different density.
I understand, but for creating ammonia, you need hydrogen.
Yeah, but for a kilogram of ammonia, you don't need a kilogram of hydrogen, because nitrogen is a very heavy atom. So hydrogen is only 1 gram per kilomole, and
Exactly.
ammonia 14. So in kilograms, you need very little hydrogen for 1 kilogram of ammonia.
Okay.
That's where it comes from. So what I use here, actually, I think it is in here. Yeah, I used €7 per kilogram of hydrogen production abroad, and €12 for production in the Netherlands. But if you make the whole mass balance, then yeah, of your ammonia molecule, very small mass percentage is hydrogen.
Yeah. And another question that I had was like, yeah, you're considering all of these costs, which are pure costs. There are some costs that are associated with being dependent on imports that are not considered in all of these cost analysis, like all the future problems that might occur, the geopolitical stuff, the cost of being dependent, right, to another country, Oman, Saudi Arabia, even US.
There are not direct costs to that. So this is just shipping costs. I think you might be referring to import tariffs. Yeah.
Or like all the possible risks that involve on being dependent on imports, right? Yeah. So like we're talking about moving all these industries outside, importing all of the fuels that we have. There are some risks and there are some costs associated.
So let's say we have the same risks as we have now, because if you look at this slide, so we barely produce anything if it comes to feedstock in the Netherlands. So this is our industry, but we import 100% of our crude oil. So yes, we're a net kerosene export country, but we're 100% feedstock import country. Same goes for natural gas at this moment. We barely produce anything ourselves. Coal, of course, we don't have any coal. So we are now, let's say, 100% dependent. If we electrify our road transport, buildings, part of the industry, and we fuel it with our own produced wind and solar power, we become a lot less dependent, much more independent. And then you have to ask yourself, for these other sectors, the chemical sector, heavy transport sector, we are dependent now. Do we want to become independent, or are we okay with the buildings, road transport, and part of the industry? So I think if you import all your molecules and electrify what you can, you are still a lot less dependent as you are now. And the question is, and that question I cannot answer, unfortunately, is that enough? Or do we need more independency? What do you think?
Personal opinion, I think the more dependency obviously is better, but who knows what's going to happen in the next. It's impossible to predict the world, even tomorrow, let aside.
Because let's make it clear, less dependency, more independency costs money. If the alternative is cheaper, import, then you have to subsidize, or do this with offtake obligations, subsidize your local production. So that costs money. And that is money that you cannot give to healthcare, education, housing, these things. That makes it so difficult to say what is enough. Thank you for the question.
Thank you for the presentation. It's a very clear story. I do have a question related to the offshore hydrogen production.
Yeah.
Because it was quite interesting to see that there's such a big increase in cost for the capex.
Yeah.
It's almost 3 times of that of onshore.
2.8. Yeah.
And I'm curious, why is that?
Very good question. So a big chunk of this 2.8 factor is the platform. Building an offshore platform is super expensive. So it has a lot of steel in it. That's expensive. But everything you build offshore, you have to transport by boats, and you have to transport people there. You have to take safety measures offshore. So this platform itself, the structure, the material, and building of it is very expensive. Then you have to install your electrolyzer offshore. That's also very expensive. Again, you need ships for this, and you need the whole commissioning and installation offshore. Let me think if there was another big chunk in this 2.8 factor. Yeah, offshore compression is, so the compression itself is not more energy intensive. That's also not within the capex, but offshore compressors are more expensive because of this marine air. How would you call this? Omstandigheden. So it's in a marine surrounding, so you have salty air, a lot of wind, birds that poop on it. And then you need extra coatings, extra protection, specifically for your compressors, because these things are very sensitive to these conditions.
Yeah, because I assume you looked at new platforms then, but you could also, because there's already quite a lot of platforms out there that you could repurpose perhaps for.
Yeah, that's been also a big study a couple of years ago indeed. So I understand why you're asking this. None of these platforms actually seemed really suited for offshore electrolysis. So if you want to do offshore electrolysis, you need 3 decks. That's for safety measures and well, mainly for safety measures actually. It needs a very specific layout, an electrolysis platform, and none of the platforms that were being looked at were actually suited enough to repurpose it. It was cheaper to build it new.
Okay, thank you very much.
Thank you for the question.
Yes, thank you for the presentation. My biggest takeaway is that the industry and the market is waiting for the government to decide which direction they're going to go. I was just wondering, do they factor in terms of emissions, the amount of greenhouse gas that is being produced with hydrogen? Because my understanding is, as a greenhouse gas, hydrogen is worse off than CO2 and other ones. So what
you need hydrogen. Hydrogen is a greenhouse gas indeed. It's the leakage, so it can leak in your system that causes greenhouse gas emissions. However, this leakage, if your system works properly, it's very, very small. So yes, you have some emissions. Yeah, not if you vent it or flare it, but that you shouldn't do. I'm really talking leakage. But this is taking into account in calculating the greenhouse gas emissions of an electrolyzer. So it's not fully zero indeed.
And also in terms of, let's say, the supply chain, the electrolyzers require rare earths on one side.
Yes. If you do alkaline, you're okay. Also, I think it's TU Delft spin-off Betalyzer, now Flexalyzer, nickel iron. PEM, however, is a very nice technology, but then you have these rare earth materials, platinum, I think cobalt as well. So I know a lot of research is being done on how to, because it's on the electrodes, right? How to make electrodes that still have a high conversion rate, but don't use these rare earth materials. I'm not sure what the current status is of this actually, but you have alternatives to PEM, alkaline and nickel iron, that do not have these rare earth materials. But conversion and efficiency goes down a little then.
So should we wait until the technology matures before committing?
No, if you want to build it here, you should just start with alkaline, maybe also some PEM, but make sure you have good legislation on how much of these rare earth materials can be on the electrodes. Make sure you set this up right from the start and start building as soon as possible. But first think of the question, do you want to produce hydrogen here? If there are no business opportunities, do you want to force them as with policies or not? And this is, I think, being thought of too little in governments. But it's a super important question.
Okay, yeah. Thank you.
Does that answer your question? Kind of.
We have a question on the other side of the room, or maybe, yeah, I'll stop. Okay. There are several questions. Let's go here.
Thank you very much for your presentation. Hello.
Flexible.
Yeah, indeed. I'm one of the, let's say, the co-founder of Electrolyzer, let's call it like that. Of course, I would be very much in favor that everybody builds big electrolyzers all over the world, and we would import hydrogen here or ammonia or whatever. But I'm afraid I don't believe it that it is cheaper. And why is that? That's because we need not only hydrogen, we also need power here. And power here is going to come from our own wind power, our own solar power. And if I look to the graphs, then I made a small calculation, I might be wrong. Behind the calculation is a high capacity factor, like wind, probably offshore wind, 45%. Behind the solar power, I see 10%.
These, so the current offshore wind parks, 45, the ones that have to come, 39. I think.
Okay, yeah, so still high capacity factors, and that is my issue there.
You think capacity factors will be lower than 39?
Exactly, because you have a lot of installed wind and solar anytime soon, and you have to be able to use it instantaneously. If you don't use it, your capacity factor of your wind and solar goes down.
Not the potential capacity factor, but actually the utilization factor. So with curtailment.
Yeah. If you don't use it, you have to curtail.
Yeah.
And of course, you can have short-term storage in batteries, all nice. But what you will see is that there is also a big seasonal effect, and you will need long-term storage as well. And there comes in hydrogen also to make our system here affordable.
Or biogas, or
biogas is very limited.
At this moment, yes, but so is hydrogen.
In the future, it's also very limited, just because of the simple reason that...
well, you need a lot of land. I totally agree on that.
Yeah, but if you look at it, our energy system today uses, let's say, fuels, emits a lot of carbon dioxide. And all of nature on the globe, worldwide, what does it do?
Absorb CO2.
Yeah, but much less than what we emit, isn't it?
Well, the speed that they absorb is much less than we emit, and that's a problem.
Exactly, and it will be exactly the same if you start chopping down every tree, use every biofuel.
If you do that with every tree, yes. Yeah. So if you incorporate too much biomass or biogas in your system, you don't get a balance. The question is, how much can you adopt without over shredding these threshold values so that the balance still exists?
Yeah,
I haven't calculated, and land is also an issue. So I'm not saying biomass or biogas is our big solution. However, I do think it's an important part of the solution. The rest could come from hydrogen or either imported.
Yeah, well, let's look at hydrogen then.
But one thing you are forgetting now, and this is the battery innovation. So I agree on the fact that we need seasonal storage, of course, and batteries now, lithium ion is not suited for that.
So how is that going to be done? That's the
two things.
question.
I think a couple of things could happen. This depends on the amount that off-takers can be flexible. So this is a question mark. We don't know how flexible all the off-takers can be. It's about the innovation in the landscape of batteries. So what is long-term storage in batteries going to do? How is that going to progress? It's about the availability of biomass and biogas. And it's about local hydrogen production and import of e-fuels. So these four things, I think, are in the solution. And what's going to be dominant, which part they're going to play, of that I'm not sure. But to say that is going to be only locally produced hydrogen, I don't think that's where we're going to end up.
Okay, so as expected, this is a topic that stimulates a lot of questions. There are still quite a lot more, but formally I have to close the official session.
Yes.
Perhaps if you still have a few more minutes, people could continue the discussion outside of the formal session, like here, maybe outside of the lecture room. So let's thank again Marjolijn Goorden for the wonderful presentation. And thank you all for being here. We'll see you at the next lunch lecture. Thank you.